In this project, I used TinkerCAD 3D modeling to design a non-electrical protective housing for a circuit system. Specifically, I designed this enclosure for an Arduino Uno R3 board, which is widely used in embedded systems and prototyping applications. The goal of this design was to create a durable, functional, and efficient enclosure that not only protects the circuit but also allows easy access, proper heat dissipation, and mechanical stability. To begin the design process, I first created a base box structure. This box included a precisely dimensioned cavity to accommodate the Arduino board securely. After that, I added internal standoffs inside the box. These standoffs act as mounting supports for the board and serve multiple important purposes. They prevent short circuits by ensuring that the board does not directly touch the base surface, provide mechanical stability by firmly holding the board in place, and also contribute to better thermal management by allowing air circulation underneath the board. Next, I improved the structural design by adding fillets, or rounded edges, to the box. From a mechanical perspective, fillets help reduce stress concentration points, making the structure stronger and more durable. In addition, they improve user safety and comfort during handling, as sharp edges are eliminated. I also incorporated precision cutouts into the design. These cutouts were carefully aligned with the USB port and the power jack of the Arduino Uno. This allows external connections to be made easily without removing the board from the housing, thereby improving functionality and usability. After completing the base enclosure, I moved on to designing the lid. I created the lid using TinkerCAD's hole and group features to ensure perfect alignment with the box. Similar to the base, I added fillets to the lid to maintain consistency and structural strength in design aesthetics. The lid was designed to fit securely onto the box, ensuring proper enclosure of the circuit. To enhance usability further, I added long rectangular cutouts on the top lid. These openings allow easy access to the Arduino pins, making it convenient to connect wires and components without having to fully open the enclosure. I also provided slight extra spacing, or wiggle room, to ensure flexibility during usage. During testing and evaluation of the design, I identified an important limitation. It was not possible to insert or remove the Arduino board through the top lid due to the protruding USB port. This created a usability issue, especially when the entire board needed to be replaced or modified. To solve this problem, I introduced an additional design feature, a thin removable back panel secured with screws. This secondary lid allows the board to be inserted and removed from the backside of the enclosure. At the same time, the top lid can still be used for quick access to the pins. This dual-access design significantly improves efficiency, saves time, and enhances the overall practicality of the enclosure. Next, I focused on thermal management. I added ventilation openings, or an exhaust system, on the top lid. These vents allow heat to escape from inside the enclosure, reducing the risk of overheating and improving the reliability of the electronic components. Additionally, I optimized the color of the enclosure by choosing a light gray shade. Lighter colors help reflect heat better compared to darker shades, which contributes to improved thermal performance. At the same time, the color also gives the design a clean and professional appearance. As a final finishing touch, I added an Arduino label on the top lid. This improves identification, enhances aesthetics, and gives the model a more realistic and professional look. Overall, this project demonstrates how thoughtful 3D design can improve the safety, usability, and performance of electronic systems. By combining structural design principles, thermal considerations, and user-centered features, the enclosure becomes more efficient, reliable, and practical for real-world applications.